Okay, so in this portion, the last portion of this lecture, we're going to discuss the gradient descent algorithm as applied to least squares. Okay, many of you might have already heard a lot about this algorithm, and many of you will hear if you have not already done so. This algorithm is extremely popular nowadays. What we're going to do is we're going to try to apply this algorithm to solving the least squares problem. Okay, well, why even do this, right? So as we're going to see, even your standard QR decomposition algorithm could actually become very difficult because the number of operations required is order of n square, and what if my n itself is in the order of 1,000,000, right? Then you actually have to spend a huge amount of time to find the least square solution, right? So is there a potentially even faster kind of a approach to this, right? Gradient descent is a very powerful technique that can be applied to solve any other unconstrained optimization problems. Okay, optimization problem is any problem that involves minimizing or maximizing something, and I'm calling unconstrained because there is no restriction on what your x can be here, right? Some other problems, for example, if you remember the min norm problem, when you have to minimize the norm of x, but you are constraining x in the sense that you are minimizing, you're allowing your variable to be only those that satisfy this equation, right? Only among those I want to find the smallest. That's a constrained problem. Here it's an unconstrained problem. So gradient descent is a technique that can apply potentially to any unconstrained optimization problem. So what is the idea here, right? So to understand the idea, let's recall that this is actually a quadratic function. Let me just take the one-dimensional and allow this to do an illustration. A one-dimensional quadratic function will look something like this, right? Let me just try to draw it a bit better so it will be easier for me. Nope. Really bad at this. Okay, so this is the quadratic function. So this is my function f of x. Let's call it f of x. So in our context, this is f of x. This whole thing, this is my f of x, right? So f of x here is ax minus b norm ax minus b whole square. Okay, here when I'm plotting, I'm just assuming x to be one variable, right? So x here is a scalar. In general, x will be a vector, and this will actually be a multi-dimensional, so it's a high dimensional plot. Okay, there will be many variables, right? The y-axis is f of x. So I want to find the minimum value of this function. Okay, and from the picture you can see that the minimum value is here, right? This is your x star. This is what you want to find. Okay. So the idea of gradient descent is, well, start from an arbitrary point, right? So pick an x0, maybe randomly, right? I don't know where x0 is. I just pick x0 somewhere, right? And then locally around x0, you move in the direction in which your function is decreasing the fastest, right? Now, what do you mean by move in the direction? Well, x0 is here because x is a scalar. Because I am on a one-dimensional space, I only have two possibilities, right? Either move to the right or move to the left, right? I only have two possibilities, right? So should I move to the right or the left? Well, that's decided easily. I cannot go to the right because my function value is locally increasing. I should go to the left. Okay, so that's the main idea, right? Of course, for more complicated functions, this may not be a good idea. For example, you could have function like this. Okay, suppose x0 is here, right? I may decide to keep moving to the left, right? And eventually I'll hit this point and I'll claim this to be the minimum potentially, right? But if you had actually decided to go right, after a short amount of time, you would have started seeing, tremendous amount of huge decrease, right? But gradient descent algorithm is actually going to miss that. Okay, so what's the main idea here? The main idea is start from an x0 and keep moving small amounts in a direction in which your function is decreasing. Okay, so here I keep moving a small amount to the left, so I keep moving a small amount, I'll go here, right? Then once again here I reevaluate, see which direction to go, right? Once again for this function you can see that I simply have to keep going left. Okay, I keep doing that. Eventually I'll hit this point, right? And at this point you see that going to the left or to the right doesn't really matter to me, right? Because at this point the derivative of the function is 0. Okay, So that's the main idea, right? You keep taking steps in the variable space that decrease your function value, okay, till you are at a point where the derivative of the function is 0. Okay, fine. So this is in the scalar case. As I said, even in the scalar case, it could run into issues with functions like these, right? So here what will happen is, I'll keep moving to the left and eventually I'll go here, and here I'll notice that the derivative is 0, and I'll not make any further movement. So I'll claim that this is my minimum, whereas in fact this is your minimum, right? Because this is an even smaller value. Okay, these are called a local minimum. Okay, and gradient descent has a tendency to get stuck in local minimum. Okay, fine. That's in general though, right? We are only interested in the least squares problem, right? In particular, let me go ahead and even put a further restriction. I am only interested when A is skinny full rank, just like before, right? A is skinny full rank. In that case, I know that there is a unique minimizer here, right? In fact, there is a unique local minimum, right? We won't have this scenario. We'll only have this scenario, okay? Because it's a quadratic, right? And ultimately quadratics look like this. Quadratics don't look like this. This is a much higher degree polynomial. Okay, fine. So that's what we are going to formalize now in high dimension. When you have more variables, right? When you have more variables, direction of steepest descent is simply the negative direction of the gradient vector. Okay. So minus gradient f of x, okay, is the direction of steepest descent. Most of you can agree with this very easily if you have done basic vector calculus. We also discussed in the first segment, right, a little bit of this, right? So any point in a high dimensional space, I simply have to move a small amount in the direction of the negative gradient. Okay, so that is basically what the iteration is. So let's formalize. I start with x0, then I define x1 to be obtained by starting at x0 and moving a small amount in the direction of the negative gradient, right? So this alpha is roughly the amount I am choosing to move in the direction of the negative gradient, right? This gradient is computed at x0, by the way. Okay, so this alpha is basically a positive parameter. It's a step size, right? So how much step I am taking in the direction of the gradient. Okay, fine. X2 is going to be x1 minus alpha grad f x1, and so on and so forth. We'll keep doing that, right? So xi is equal to xi minus 1 minus alpha grad f xi minus 1. Okay, I equal to 1, 2 up to infinity. This is the iteration for gradient descent. Okay, so alpha is the step size. It's also called the learning rate for reasons I will not go into. So alpha is called the learning rate or the step size. The choice of alpha is crucial. Typically you will want alpha to be not too big, right? If alpha is big, that could lead to a lot of zigzagging. For example, let's take a very simple, square function. So let's say that I am trying to minimize this function f of x equal to x square. I'm trying to minimize this, right, trivial function, right? And I start at x not equal to 1. This is x not equal to 1. I start here, okay, and suppose I pick alpha to be 1. We'll see what the gradient descent will do, right? I hope I have picked the right values, but okay, fine, let's see. So what will gradient descent? The gradient descent will say, well, I start here, let me compute the gradient of the function. It's a single variable function, so the gradient will simply be the derivative, right? So x not equal to 1, according to this equation, I'll find x1 to be x naught, which is 1, minus alpha, which is 1, times the derivative, which is 2. Okay, correct? So the derivative of the function at 1 is 2, right? So that is going to give you minus 1. So I'll actually end up here, minus 1. Well, apply once again. What will happen is that you'll see that x2 will be x1 minus 1 minus alpha times minus 2. Well, alpha is also 1 here, and you will get minus 1 again, right? So your algorithm will just keep on oscillating between 1 and minus 1. Okay, in some sense alpha is too large. You are taking too large of a step, right? Too large of a step. So you're simply overshooting your minimum, and you're ending up on the opposite side, and you keep doing that. You keep oscillating like this. You never actually hit the minimum. Gradient descent will not even converge, right? So typically alpha has to be small enough. we'll formalize this for our problem in a minute, right? Alpha has to be small enough. Okay, so the issue is the choice of alpha, right? What alpha do I pick? And ultimately the issue is how fast do I actually converge, right? Because this is an iterative process. Unlike the other process that we have seen till now, this is an iterative process that you hope eventually will take you to the minimum, right? How long does it take you to get there? Okay, so that's the main issue. Okay, fine. So let us say that we did use gradient descent and everything worked out well. Let's just try to do a basic analysis on the number of computations required in each step of gradient descent. Okay, fine. So basically gradient descent is one of those algorithms that assumes that you can readily compute the value of the function and the gradient of the function at any x. Okay, like on demand, whatever x you give, I should be able to compute f of x and grade f of x. If I know these, then I can just keep doing gradient descent. By the way, when do you stop these iterations? You stop these iterations when you think that the derivative is 0, meaning the gradient is close to 0. Okay, so this gradient is a vector typically. So when the gradient of the vector is small enough, right? So it says smaller than eta. Eta is some threshold you set, typically very small, like 10 to the minus 3, 10 to the minus 2, whatever, depending on your stopping level. There is some argument to be made for stopping gradient descent early in some scenarios. That's for later anyway, right? Anyway, so you can actually take take some threshold and stop when your gradient is smaller than the threshold. The norm of the gradient is smaller than the threshold. Okay, so that's when you stop. So let us try to see what is the gradient actually for our problem, the least squares problem. Okay, fine. To find the gradient of any function, you have to find the partial derivatives and all that stuff, right? But let's not do that because multivariable calculus get a bit messy. Our problem is very simple. So what I'm going to do is I'm going to use this idea, right? So remember, what is the idea of a derivative, right? So when you have a function f of x plus h is approximately like f of x plus h times f prime x plus h square times f double prime x plus so on, right? Well, approximate because let's say you choose to stop after the second step. Well, it's a second order approximation, right? This is the Taylor series basically, the second order Taylor series approximation, correct? So basically, if I am able to write f of x plus h as a series like this, then I can read off the coefficient of h as the derivative, right? I can do similar thing for multivariable stuff. So let's say you have f of x plus y, x and y are vectors, and you can write it as f of x plus this first order term here becomes gradient of f transpose times y. Okay, or let me just write it like this: y transpose grad f of x plus the third term becomes something like y transpose some matrix times y. Okay, something like this. So if I am able to write my function like this, I can simply read off the gradient as whatever comes here, right? So let me adopt that approach. It will be much simpler. Okay, so what is my f of x here? Just recall f of x is ax minus b whole square. Okay, so let's do f of x plus y, that is ax plus y minus b whole square. Okay, so I'm going to leave it as an exercise to actually expand this out. Okay, I'll put this in the assignment. Leave it as an exercise to expand this out, and you'll actually get that this is equal to y transpose a transpose ay, okay, plus y transpose a transpose ax minus b plus f of x. Okay, leave it as an exercise to do it, but it's just basic expansion like what we have been doing all this course. I think I discussed a bit of this in the first segment as well, right? But you can just expand it and you will get this, right? There's nothing much to it than that, right? So this forms your square term, okay, like here, this forms your square term, this forms your linear term like here, and this forms your f of x, your function f of x. So you can simply read off the gradient as grad f of x is equal to a transpose times ax minus b. Oh, by the way, there is a factor of 2 here. I always keep forgetting that, minus b. Okay, so 2a transpose times ax minus b. This is your gradient. Okay, so how many computations are required to find the gradient? Because it turns out, right, in each step, all I need to do, it would seem, is to find the gradient. right? If I find the gradient, I multiply by alpha and then change it. This operation here, x is an n-length vector, so this is just n, order n operation, right? Finding the gradient itself is going to be probably costly. So how much does it cost to find the gradient, right? Okay, so to find the gradient, I have to find ax minus b. B is an m cross 1 vector. To find ax, I'll take order mn operations. Okay, and then to subtract a b vector, we'll take order m operations, right? So let's just do something like this, order m operations, and then to multiply with A transpose, we'll take another order mn. Okay, so that's what is the gradient going to be for me, right? I mean, that's pretty much it. So it's just going to be order mn. Okay, so each step of gradient descent does order mn operations. Okay, contrast this with the earlier solutions. We needed order mn square, but that gave you the full solution directly. Here it's an iterative process and each step takes order mn. Okay, so if you get lucky and the gradient descent converges very, very fast, then you can potentially get to less than order mn square. Potentially, maybe, right? So for that, we need to address the issue of how fast this converges. Okay, fine. So I hope this much is clear to everybody. I've just set up the basic here, so now what we'll do is we'll just try to get a preliminary idea of how does the gradient descent algorithm converge, right? What does it depend on, really, right? Like what attribute of the matrix A does this convergence depend on? Okay, fine. So to do that, let's actually go to this step, right? So let's write down this equation. This is the iteration step ultimately, right? Okay, so let's write it down. I'll rewrite it here. Xi equal to xi minus 1 minus alpha times grad f of xi minus 1. Okay, now we have a specific expression for grad f, so I'm writing this just to get an idea of how fast the convergence goes. Okay, minus alpha times, we write the gradient here is going to be A transpose Ax minus b. Okay, just rewriting, so this is xi minus 1. Okay, A transpose Axi minus 1 minus b, that's how it's going to look like, correct? Okay, so let me do just a little bit of rearrangement of terms, and I'll write it like this: minus alpha A transpose A multiplied with xi minus 1 minus plus alpha A transpose B. That's what it will be. This is going to be xi. Okay, so effectively what's happening is this is some matrix M that I have here, right? So it's like, I'm taking the vector x and I'm multiplying it with some matrix M. Okay, and I'm adding some constant. This term gets added to every x, right? It doesn't change with iterations, right? Basically what I'm doing is I'm taking the output of the previous iteration, multiplying it with a matrix and adding a constant. Okay, so if x were a scalar, effectively what you would be doing is like this, right? You would be doing xi is equal to some m multiplied with xi minus 1 plus some constant c. That's basically what you're doing here, right? So x naught mx naught plus c will give you x1. Then you multiply this further with m and add c, that will give you x2, right? So x2 will be like m square x naught plus mc plus c, right? X3 will be obtained by multiplying this whole thing again with m and adding a c. So that's going to be like, m cube x naught plus m square c plus mc plus c. Okay, correct, right? So in general, you're going to get some summation like this, right? You're going to get m to the I x naught xi to be m to the I x naught plus c times summation of m to the k equal to 0 to I minus 1 times c, something like this you'll get. Okay, same thing will happen with matrices, right? There's nothing really different. The algebra and all stay the same. So what you get is xi to be, you'll get matrix powers here, m to the I x naught, right, plus some similar property, right? Summation of m to the k equal to 0 to I minus 1 times alpha A transpose, something like this you will get. Okay, fine. Okay, so what does it mean for this to converge, right? What does it mean for this to converge? Well, here in the scalar case, right, if this has to converge, then at the very least you need m to the I to go to 0 as m goes to infinity. Correct? So here also we will need a very similar property, right? So we'll need this matrix m to the y at the very least. Okay, at the very least need m to the I to go to 0 as I goes to infinity. This is because, well, x0 is your choice, right? You want to pick, no matter what x0 you pick, you want to end up with your answer. Okay, you want to end up at the minimum. In particular, x0 should not play any role on which answer you get. Okay, that means whatever factor is multiplying x0 must go to 0 as you take more and more iterations, right? I here is the iteration index. Correct? So we definitely need this, okay, for convergence. Okay, so when does this happen? When does the power of a matrix keep going to 0 as I goes to infinity? So in the matrix norm lecture we discussed that this is actually equivalent to saying that the spectral radius of M must be less than 1. Okay, the spectral radius of M is the largest absolute eigenvalue, okay, of the matrix. Correct? The spectral radius of M must be less than 1. Okay, so that's the equivalent condition. So we need to ensure that. Okay, well, what is the spectral radius of M? To get that answer, we need to know what are the eigenvalues of M. Right? So let's recall what M is. The matrix M was this one, right? I minus alpha A transpose A. So let me write that down here. It's going to be I minus alpha A transpose A. Okay. Okay. So suppose the eigenvalues of A transpose A are like lambda 1 to lambda n. Let us assume in ascending order. So lambda 1 up to lambda n. These are the eigenvalues of A transpose A. Okay. Fine. So what are the eigenvalues of M then? Right? By a simple operation, you can very easily see the symmetric matrix here. It has n eigenvalues. Well, yeah, n real eigenvalues. M is also a symmetric matrix. So the eigenvalues of M are simply going to be 1 minus alpha lambda n, 1 minus alpha lambda n minus 1, so on up to 1 minus alpha lambda 1. Okay. So this will be the smallest of the eigenvalues. And this will be the largest. Right? Because lambda 1, like these are arranged in ascending order, so the ascending order of eigenvalues of M will be this one. Okay, fine. So that those are the eigenvalues of M. So you want the spectral radius to be less than 1. Okay. Okay. So what does that mean? That means, first of all, that means that all these eigenvalues must be between -1 and 1. Okay, so remember, spectral radius is the largest absolute eigenvalue, correct? So this is like saying all eigenvalues must be between -1 and 1. Between -1 and 1. Okay, fine. So that means that, you know, -1 must be less than or equal to this, less than or equal to 1. Okay, so the smallest one of these must be at least -1. The largest one of these must be at most 1. Okay. So what does that give you? Let's look at this one. The smallest one is at least -1. That tells you that alpha lambda n must be at least must be at most 2. Okay, in fact it's a strict inequality, so I should not even have less than or equal to here, right? Because remember, we need spectral radius to be strictly less than 1 here, right? Okay. So alpha lambda n must be less than 2, right? In particular, that means that alpha must be less than 2 by lambda. Okay. So remember, what this is telling you is an upper bound on the step size. It's telling you that the step size cannot be too large. We knew that anyway, right? We knew that if you have a large step size, you could get oscillation, right? This is telling you precisely how large the step size should be. It's at most 2 by lambda n. Okay. So alpha must be less than 2 by lambda n. And this one, if you look at the next term over here, that just says that, you know, alpha lambda 1 must be bigger than 0. But that's true anyway, right? Alpha is a positive number, so step size, and lambda 1 is also positive. Why is lambda 1 positive? Because we are assuming this is first of all a gram matrix, so all its eigenvalues are going to be non-negative, and I'm assuming it's full rank. A is full column rank, right? So this whole thing is going to be full rank, so lambda 1 will be positive. Right, so anyway, this will also be satisfied. This will be trivially satisfied. I don't have to worry about that. So this is the only one that I have to ensure. This is directly putting a bound on the step size of the learning rate, telling you that it must be 2 by lambda. Okay, fine. But I also don't want to pick learning rate to be close to 2 by lambda n. I don't want to do that, right? Because if I pick it to be close to 2 by lambda n, then this value over here becomes close to -1. Then the spectral radius becomes close to 1. So remember here that m to the I goes to 0 if the spectral radius is less than 1. How fast it goes to 0 depends on how small this is compared to 1. Okay, so just like when you have a to the power of n goes to 0 as n goes to infinity, right? This is true when a is between -1 and 1. When a is between -1 and 1, right? Just like spectral radius. This is true if a is between -1 and 1, right? The rate of convergence will be very fast if a is close to 0. Right? That means if a is very very far away from 1 or -1, the rate of convergence will be very fast. That's what you want here, right? For your gradient descent to converge fast, you don't want these spectral radius to be close to 1 either. Okay, so you don't want this to be close to -1. You don't want this to be close to 1. Okay, so you do want to keep some gap here. Okay, so let's define some parameter here. Let's say C to be alpha lambda n. Okay, so this multiplication I'm defining as C, right? Then we need C to be less than 2. Okay, of course C is also at least 0 because C is alpha lambda n. Lambda n is a positive number, alpha is a positive number. So C is some number between 0 and 2. Okay, setting C is the same as setting alpha. Okay, fine. Okay, fine. So I define this C. Okay, then in terms of C, so C is the parameter I will control now, right? And C I will keep between 0 and 2. In terms of C, what are the eigen values now? Okay, this quantity here is simply 1 minus C. Okay, so the eigen values here will be 1 minus C, right? The next style here 1 minus alpha lambda n minus 1. I'm going to write it as 1 minus alpha lambda n 1 minus C lambda n minus 1 by lambda n. Okay, I'm going to write it like that. Okay, the next eigenvalue is going to be 1 minus C lambda n minus 2 by lambda n, and so on. The largest eigenvalue is going to be 1 minus C lambda 1 by lambda. Okay, that's what it's going to be, right? Now the reason I'm doing this is because I need to know what is the spectral radius, what is the largest absolute value in eigenvalues. Okay, fine. So if I drive, the thing to remember here is that if I drive C, if I drive C close to 2, as I was saying before, then the spectral radius becomes this term, right? But if I keep C to be very small, let's say I keep C to be 1, not small, but let's say midway, I keep C to be 1, then this term here will actually be 0, right? But this term here will be something like 1 minus C times lambda 1 by lambda n. Okay, C is 1, so it's just going to be lambda 1 by lambda n. 1 minus lambda 1 by lambda n. What is this quantity here? This quantity here is the smallest eigenvalue by largest eigenvalue. It's actually equal to 1 over the condition number of the matrix A. Condition number of A transpose A, sorry, not A. That's the condition number of A transpose A. Okay, so 1 minus the condition 1 over the condition number of A transpose A. So let's say A transpose A is very poorly conditioned, right? So condition number of A transpose A is, let's say, 100, right? Then this quantity over here, this eigenvalue is like 0.99. Okay, so even though I picked C to be 1 to avoid this eigenvalue dominating the spectral radius, right? This eigenvalue just becomes 0 if I pick C equal to 1. Okay, but now this eigenvalue over here ends up being very very close to 1. Okay, it's 0.99. It's actually very very bad, right? It means my convergence is going to be very very slow. On the other hand, let's say this condition number was very nice, meaning that A transpose A condition number is like 2, like it's a very good condition number. Then in that case, you can see that this value is going to be 0.5. Okay, and that will ensure that gradient descent will converge, or at least this quantity will converge to 0 very fast. Consequently, gradient descent also will converge very fast. Okay, so the convergence of gradient descent, as you can see, depends on the condition number of A transpose A, right? To be precise, you can write the condition number of the matrix M involved is max of 1 minus C, comma 1 minus C by condition number of A transpose A. Okay, that is going to be the condition number of M. Okay, so this, how large, what is this, depends on max of absolute values. That's important, otherwise it's kind of trivial. Yeah, max of absolute values. Okay, so convergence depends on the condition number. Okay, remember C is a parameter of your choice, right? I can easily avoid C to hit the, so I to avoid 1 minus C from being close to minus 1, remember this quantity over here is like less than or equal to minus 1, and this quantity here is less than or equal to 1. I can readily avoid this gap. Okay, again, it's not less than or equal to, it's less than, yeah. I can readily avoid this, right, by simply picking C to be far away from 2. Don't make C to be 2, right? But then this quantity I have no control over, it depends on the condition number of the matrix. This whole thing can still end up being very close to 1, and thus making the spectral radius of M close to 1 and slowing down the convergence of gradient descent. Okay, so convergence depends on condition number of A transpose A. Okay, smaller the condition number, faster the convergence. Okay. Okay, so that's the key idea here. We are not doing an exact analysis here. This is just like, a rough idea, roughly telling you how condition number actually comes into play even in convergence of gradient descent. Okay, but in the assignments, if everything works out and time permits, I'll put a guided sort of a walkthrough on doing a more precise analysis of gradient descent for least squares algorithms. So in general, if n is very large, then the recommended method is to use gradient descent to solve least squares. Okay, not even QR, gradient descent if n is large meaning it's like really 10 to the 5 or 10 to the 6 order, right? You might have seen basic machine learning lectures. They actually do talk about this, but they don't do the analysis that we have done here, right? Okay, so we will stop here. As I said, for those who are interested, we'll take this up in the assignment. Okay.